Hi students, myself Professor Amapan, Assistant Professor in Physics, Government for State College, Namanara, Bagalkot, affiliated to Rani Channama University of Belagavi. So here I am dealing with a fifth semester, second chapter, so which is wave mechanics. Your fifth semester syllabus, physics syllabus contains five chapters. First one is quantum mechanics. Second one is the wave mechanics. The third is atomic structure. The fourth one is molecular structure. And the last one is mathematical physics. So in these five chapters, the chapter allocated to me for fifth semester is that is wave mechanics. The syllabus contains that wave mechanics contains the Schrodinger wave equations. The physical significance are the interpretation of wave functions and applications of Schrodinger time independent wave equations in one-dimensional box and linear harmonic oscillators, and it contains a certain problem on that chapter. Okay. So today, in the first session, so we will derive your Schrodinger a time independent wave equation. So before deriving these equations, let's discuss how that wave mechanics came into existence. So far, we have seen in your first chapters, so that is what it is, macro waves. The concept of macro waves was proposed by our scientist G. Broglie in 1928. Okay, so according to him, every material particles exhibits a wave nature. The wave is associated with what? Material particles are called as de Broglie waves, or it is simply called the what? A macro wave. This is a hypothesis produced by our scientist de Broglie. So based on that, so he has derived an equation. So the wavelength associated with what? Photon is given by lambda is equals to h divided by what? P, lambda is equals to h divided by what is m into waves. So for an electron, the wavelength associated with electron, that is also elementary particle. So each, all the material particles or elementary particles exhibits in what? A wave nature. That is the concept predicted by our scientist de Broglie. Okay. For an electron, the wavelength associated with the electron is given by lambda is equal to what? H divided by root of 2m into capital E, or instead of capital E, you can write small e into capital V. So A is the magnitude of the charge of the electron, and capital V is the what? Is what? The voltage, the potential difference that you are what? Applying across this instrument in order to accelerate the uh, velocity of the electron. Okay. So later, uh, the wave nature of the electron was demonstrated by two scientists. G.P. Thomson, for the first time, G.P. Thomson, Davidson and Germer together demonstrated the what? Wave nature of the electron, and later another scientist who confirmed that wave nature of the electron was G.P. Thomson. Okay, so those two scientists what demonstrated the is it our electron exhibition what wave nature or not. Okay, and later, so you were having uncertainty principle is. So in case of your uncertainty principles, it is not possible to determine simultaneously both position and momentum of the particles accurately when that wave is associated with what any elementary particle or the particle is associated with what waves. Okay, so with the help of this one, what I'm saying is we have seen that wave-like characteristics could be associated with what material particles. That means wave is associated with our what material particles like electron, proton, and neutron. When we say that wave-like characteristics is associated with your what elementary particles such as electron, proton, and neutron, then in 1926, it is what Irvin Schrodinger developed an equation for the what a wave associated with that these elementary particles. When we are saying that a wave-like characteristics what is associated with our what material particles, then that wave is having a certain equation. So that was predicted and derived by our scientist Irving. So that equation is what it gives. That equations could describe the what the behavior of the particles, and whatever the solution of that equation is there, the solution of the wave equation should describe the what particle aspects, wave aspects, so as well as what, but also consistent with the what uncertainty principles. So that the use of what Schrodinger equation. Okay. Uh, there is a one term, that one variable is that describes everything inside that concept is. So that term they have mentioned is what is wave function. So we know that due to the variation of pressure, a sound wave is what produced. In the same way, the electromagnetic waves are characterized by the what variation of electric and magnetic field. Okay. In the same way, the variable quantity, one physical quantity, that one variable quantity, so which describes the what de Broglie waves is called as what wave function, and that was denoted by a symbol of what sounds. But the use of this wave functions already have mentioned in the definition itself. The wave function is describes the variable quantity which describes the what de Broglie waves, which called as what wave functions. So here the value of the wave functions associated with the what a moving particle, that is what is existing is associated with what a moving particle at a particular point in space at a time t finds the particle at that time with the use of what wave functions. Okay, so let us derive that your what time independent Schrodinger wave equations. So here, so we are having a two that Schrodinger has derived and what equations for time independent as well as time dependent. But in your syllabus, they have mentioned what is time independent Schrodinger wave equations. Okay. So in the first session, so we will derive and what the Schrodinger time independent wave equations. Okay. So let's see how that equation is what derived, and I already have mentioned that. So what is the dual nature of your light? So in the first chapter, so in case of your matter waves, so you know to explain that matter waves, there you have learned that light exhibits a dual nature wave as well as what is particle in nature. So now we explain interference and whatever that your diffractions and reflections are there. So for all those phenomena, so we treating the light as a what? Wave. While explaining your fountain effect and the photoelectric effect, So we are treating that light as a what? Particle. So that we are confirming that light is what? A wave, dual nature. Okay. Next, already I mentioned that your matter waves and what you mean by kinetic energy is nothing but what? The energy possessed by our particle with its what? Motion. And we know that your Newton's second law of motion. So I have written that Newton's second law of motion. So we will confirm this, whatever the Schrodinger time independent equation is that in wave mechanics is that you say is similar to that of what Newton's second law of motion is in our classical mechanics. Okay, so that is equals to what AMA in our second law of motion. Okay, already I have mentioned that what is your de Broglie waves and what is that your wave functions. De Broglie is the what? Wave associated with our moving particle. It's called as de Broglie waves, or it is also called as what? Matter waves. So wave functions is nothing but what? The variable quantities. One quantity is existing in a what way? So that will describe the what? Your de Broglie waves. So it's called as wave functions that gives a complete information, complete physical information regarding the what? The particles which is associated with what? Wave. Okay. So we know that the differential equations in the three-dimensional motion is represented by. So what I'm saying is, so it's given by dou square psi divided by dou x square plus of dou square psi divided by dou y square plus of dou square psi by dou z square is equals to dou square. It is psi divided by dou t square into 1 by v square. So we know that in the our slide, I mentioned that this equation is similar to that of Newton's second law of motion in what classical mechanics. In what rule? The second law of motion, Newton's second law of motion played in a rule in classical mechanics in the same way that our what Schrodinger equations will play plays in the same rule in the wave mechanics. Okay. So according to de Broglie's, the wavelength associated with the particle is given by that lambda is equal to what? Equivalent by into v. A particles which have the what properties of waves. When you are saying that the particle exhibits in a wave nature, then it's having it exhibits then it's having what some sort of equations. That equations describe what the physical behavior of that particle. Okay, so here the differential equations in three-dimensional motions is given by dou square psi by x square plus dou square psi by y square plus of dou square psi by dou z square is equal to what? Dou square psi by dou t square. So in 1 by dou square. So whatever already I have mentioned that what is the wave function? That wave function is what? That is a variable quantity which will describe the what? The heat of waves. So here that particle is existing in a three-dimensional space. So that's why the wave function of what's the wave function of that particle? So in x, y, and the direction. So that's why. So your in three-dimensional motion it is given by like this. Okay. So here so this dou square by dou x square plus dou square by dou y square plus of dou square by dou z square. So is nothing but your what is uh, is nothing but here we are designated by a symbol of what del square. Del square psi is equal to what dou square psi divided by dou t square into 1 by this the value of del square. The is given by what gradient del square equals to dou square by dou x square plus of dou square by dou y square plus of dou square by dou z square. So here psi is Already I mentioned that is a wave function which undergoes and what periodic changes. Okay, the value of that wave function at time t, is given by whatever that value of that wave function is there. So in space, for that particle is given by psi is equals to psi naught into sine of what? 2 pi mu into psi. Where so psi naught is the what? A constant of what? Amplitude, which is independent of time, but it is what is a function of x, y, z and a frequency. So this one, whatever the psi naught is a constant. Amplitude of constant is independent of time. So that's why. So here that heading is the time independent Schrodinger wave equation. But the amplitude of that wave function is depends on the what? Is the functions of x, y, z and the frequency as units. Okay. Now, so simple derivation is that let us differentiate your equation 2 respect to t. So twice. So we get what? When you differentiate, so those with respect to t, dou tau by dou t phi naught into differentiation of sine 2 pi is cos of 2 pi is there. Again, you want to differentiate this quantity because it contains the variable t is there. So differentiation of 2 pi is what? Simply 2 pi nu it. Okay. So next, those square sine by dou t square is equals to what is phi naught. Right as 2 pi nu into bracket differentiation of cos is minus sine 2 pi nu t. So that bracket into 2 pi is what? Nu it. That is equal to minus of 4 pi square nu square. Is what is psi. Okay. But we know that psi is equal to what? Psi naught. Sine of 2 pi t z. So this instead of this one, so you want to impose the term sine. Okay. So we got what? The value of dou square sine by dou t square is equal to minus of 4 pi square v square and nu square into what sine. But in your other equations, so del square sine equals to what? Dou square sine by dou t square into 1 by v square is there. So you have the values of what? Dou square sine by dou t square is there. So that equals to what? The insert from this equation. So you will get 1. So dou square sine equals to 1 by v square into minus of 4 pi square v square into sine. So that is equal to minus of 1 by v square 1 by v square into 4 pi square. But the frequency nu is equals to what? This is velocity divided by lambda wavelength. So you know that in the previous class. This is frequency of our what? Particle. That's the velocity divided by wavelength. So here mu square is there. That's why we're getting what? Mu square by lambda square into right what? Sine. Okay. Next, del square sine equals to minus of 4 pi square sine. Here you make it cancel. This v square and v square you make it cancel. So you get minus of 4 pi square sine into 1 by lambda square. So del square sine equals to 4 pi square sine into what? You take this term to the left hand side, you can put plus by lambda square equals to what is 0. It becomes 0. Next, del square sine plus of what? 4 pi square sine. But we know that lambda is equal to what? According to the Brownian equation, lambda is equal to what? M into V is there to make it square. Okay. So this equation becomes what is del square sine plus of what? 4 pi square m square v square into sine divided by x square equals to 2. Okay. So let's say this equation is what? 4 points. But let's assume that if E is the total energy of the particle, which is associated with what? Wave, and V is what? The potential energy of that particle. Then its kinetic energy is given by half m square. You know that total energy is equals to kinetic energy plus potential energy. But here we require kinetic energy equals to capital E minus of what? And capital V. Okay. So multiplied by m on both sides. So we make it cross multiplication m square v square equals to 2m into bracket what? Capital E minus of what? Capital V. Substitute this value in equation number 4. So you will get what? Del square sine plus of what? 4 pi square 2m into bracket what? Capital E minus of what is capital V into sine divided by what is okay. When you substitute that equation, So you are getting what? It becomes what? 8 pi square m into bracket capital E minus B into psi divided by what is x square. So del square psi plus of what? 8 pi square m into bracket what? Capital E minus of capital E into psi divided by x square is equal to 0. So this equation is the what? Three-dimensional Schrodinger time independent wave equation. Okay, so where already I have mentioned that del square is equal to dou square by dou x square plus dou square by dou y square plus dou square by and dou del square. Suppose if you want to write this equations on an what? One-dimensional box, the particle exists in what? One-dimensional way. So you can write it simply it becomes what? Dou square sine divided what? Dou x square plus of what? 8 pi square m into bracket capital E minus capital V divided by x square into psi equals to 0. So this is the what? Time independent Schrodinger wave equation in what? Three dimensions of wave. So we can put it one dimensional, two dimensional, and what? Three dimensional. But this one is in now it is in what? Three dimensional. But in one dimension it becomes what? Simply dou square psi by dou x. Okay. So this is a okay already. This here I written that for one dimensions it is given by dou square psi by dou x square plus 8 pi square m into bracket what? Capital E minus of what? Capital V divided by x square into psi. Okay, what is and okay. So this is about a simple derivation regarding your what time independent Schrodinger wave equations. Okay, so in this first session, I discussed regarding what we mean by how that wave mechanics it came to exist and even what is the wave function when that particle exhibits in a wave nature, when that particle is associated to wave, when that material particles exhibits wave nature, that wave is having what some expression. So that equation was derived by our scientist Schrodinger. That first particular was just the Hamilton what time independent Schrodinger wave equation. Okay, so that's a simple derivation of what Schrodinger time independent wave equation. Okay, in the next class. So we will discuss about what is the physical significance of the what of the waveform.